Okay, so I was just about done. Just to finish this last few slides here. So there's numerous reasons why the spectral lines can broaden, and we're going to look at those right now. So I'll just go over this real quick. So with whatever the peak wavelength is, if you know, by looking at the spectra, you can figure out what the peak wavelength is. That's of course this point right here. I know it says frequency across here, but you can also, look at the wavelength. If you know the frequency, you can always calculate the wavelength. Anyhow, that'll give you the temperature. That's called Wien's law. What particular lines are present will give you the composition, and of course, what the temperature is as well. Of course, the temperature is, you have to use Wien's law. The intensity of the lines will actually tell you something about the composition as well. Basically what the relative the relative composition is. You should really say relative composition. So, for example, if you look at a star and you know that 70% of that star, like our sun, for example, is made of hydrogen, and roughly 25%. It's not exactly the number, but roughly 25% of it is made of helium, and then you can figure out what's the rest made of. How much element of the element oxygen is there, how much carbon is there, and so forth. That's the way that you can look at all of the the different elements. And of course, to some extent, what the molecules are, if they're not really complicated molecules. All right, so when the lines widen, however much they widen, and we're going to look at that, down here, how much the lines widen can tell you something about whether there's turbulence. I know I mentioned this in the last video. Whether there's turbulence, what's the rotational speed of the actual atoms or molecules, the density, and sometimes you can actually measure the magnetic field, and that's actually a quantum mechanical effect. We can you can't see that with all objects in the night sky. For example, the sun. We can do this when we do the spectral analysis of the sun. We can do the spectral analysis of Jupiter as well, and measure the magnetic field. The other thing, of course, is the shift. So when we look at the spectral lines themselves, they either move to the red end of the spectrum or red shifted. That means, of course, whatever this object that we're looking at is moving away from us. If it's blue shifted, we can tell whether it's moving that it's moving towards us, and the amount of red shift or blue shift tells us how fast it's going. So we can actually measure that. All right. Now it doesn't tell you how fast it's moving if it's moving perpendicular to our line of sight, right? If it's going like around if it's a one star going in a perfect circle around another star, we can't, using the Doppler shift, you can't measure that. All right. It has to be moving towards us or away from us, or some part of the motion has to be moving towards us or away from us. All right, so the Doppler shift can broaden the lines, or make them wider. All right, so and then also the rotation of the individual molecules can cause the lines to widen as well. And I was really close to being done in that last video. So this is just a summary of what we just talked about. All right, so that is it, and I will talk to you about Chapter 5 with the next set of videos.